consider three-dimensional space. So we have our x, y and z coordinates. X, y and z. And suppose we consider rotation about z-axis, anti-clockwise rotation by an angle theta about z-axis. Now a rotation is a linear transformation, so corresponding to this rotation we will have a 3 by 3 matrix, and we want to know what this matrix is. For this, first of all, note that since we are considering rotation about z-axis, so if we take any vector along z-axis, then this rotation will not change that vector. In particular, if we take the unit vector 0, 0, 1 along z-axis and we apply this rotation on this vector, then we'll again get back 0, 0, 1. Now suppose we consider the unit vector along x-axis, which is the vector 1, 0, 0. This vector under this rotation will change to a new vector which will again lie in the x, y plane, and its length will still be 1, and this vector will make an angle theta with the x-axis. So its x component will be cos theta because it is of unit length. Its y component will be sin theta, and its z component will be 0 because we are considering rotation about z-axis, so the vector remains in the xy plane. So we will have r theta z acting upon 1, 0, 0 will give a new vector whose x component is cos theta, y component is sin theta, and z component is 0. Now if we consider unit vector on y-axis, if we take unit vector on y-axis, then under this rotation it will change into a vector which will still lie in the xy plane, and it will still be of length 1, and it will make an angle theta with the y-axis. So this vector, its y component will be cos theta, its x component will be sin theta in the negative direction, that is minus sin theta, and its z component will be 0. So we will have r theta z acting upon 0, 1, 0 equal to minus sin theta cos theta 0. Therefore, we can now write our rotation matrix r theta z, whose first column is this vector cos theta sin theta 0, second column is this vector minus sin theta cos theta 0, and its third column is this vector 0 0 1. Now suppose in this matrix we expand cos theta and sin theta in their corresponding Taylor series. We are doing this in order to find the infinitesimal transformation corresponding to this rotation. So we write cos theta and Taylor series of cos theta and sin theta. Taylor series of cos theta is 1 minus theta square by 2 factorial plus theta 4 by 4 factorial minus theta 6 by 6 factorial and so on. Similarly, for sin theta we have only odd power terms of theta, so we have theta minus theta cube by 3 factorial plus theta 5 by 5 factorial and so on. Then we have 0. Then again we have Taylor series for sin theta, theta minus theta cube by 3 factorial plus theta 5 over 5 factorial and so on. Then we have 1 minus theta square by 2 factorial plus theta 4 by 4 factorial minus theta 6 by 6 factorial, and then 0 0 0 and 1. Now we write this as an expansion in powers of theta, as a series in powers of theta with coefficients as matrices, constant matrices. So the first term is the constant matrix, which is the coefficient of theta to the power 0. In the 1 1 term, the coefficient of theta to the power 0 is 1. In the 1 2 term, it's 0. In 1 3 term, coefficient of theta 0 is 0. In 2 1 term, it's again 0. In 2 2 term, the constant term is 1. In 2 3 term, it's 0. Then we have 0 0. And in 3 3 term, the constant term is 1. So we get the identity matrix. Then we consider the matrix which is coefficient of theta term. In the 1 1 term, the coefficient of theta is 0. In 1 2 term, coefficient of theta is minus 1. Then in 1 3 term, coefficient of theta is 0. Then in 2 1 term, coefficient of theta is 1. 2 2 term, coefficient of theta is 0. Then we have 0 0 0. In 3 3 term also, coefficient of theta is 0. Then we consider theta square by 2 factorial. In the 1 1 term, coefficient of theta square by 2 factorial is minus 1. In 1 2 term, coefficient of theta square by 2 factorial is 0. Then 0 0. In 2 2 term, coefficient of theta square by 2 factorial is again minus 1. Then 0 0 0 0. Then we consider coefficient of theta cube by 3 factorial. In the 1 1 term, coefficient of theta cube by 3 factorial is 0. In the 1 2 term, it's 1. Coefficient of theta cube by 3 factorial in 1 2 term is 1. Then we have 0. In 2 1 term, it's minus 1. Then we have 0 0 0 0 0. Then coefficient of theta 4 by 4 factorial. In the 1 1 term, it's 1. In 2 2 term also it's 1, and everywhere else it's 0. And so on. Now in this series expansion, if we denote the coefficient of theta term, this matrix which is coefficient of theta, as Jz, then we notice that the coefficient of theta square by 2 factorial is nothing but it's jz square, the square of this matrix, and the coefficient of theta cube by 3 factorial is jz cube, and coefficient of theta 4 by 4 factorial is equal to jz 4. So we can write our series expansion as identity matrix 3 by 3 identity matrix plus theta jz plus 1 by 2 factorial theta square jz square plus 1 by 3 factorial theta cube jz cube plus 1 by 4 factorial theta 4 jz 4, and so on. And this series is by definition of the exponential of a matrix, this series is exponential of theta jz. So this is the definition of exponential of a matrix, and if we take exponential of theta jz, then by definition we get this series. So we have written our rotation about z-axis by an angle theta as exponential theta jz, where jz is the matrix 0 minus 1 0 1 0 0 0 0 0. This matrix, which when exponentiated gives a rotation, is called infinitesimal generator of this rotation. So it is infinitesimal generator of r theta z. In physics literature, instead of writing our generator as a real antisymmetric matrix, we usually write them as Hermitian matrices. So we define a new matrix jz cap as I times jz, and this matrix is 0 minus I 0 I 0 0 0 0 0. And in terms of this matrix, our r theta z, this rotation, becomes exponential minus I theta jz cap. Because jz cap is I jz, so minus I and I when multiplied will give 1, so we get the same expression as we have derived before. So r theta z is equal to exponential minus I theta jz cap. Similarly, for rotations about x and y axis, if we consider rotation about x axis by an angle theta, it can be written as exponential minus I theta jx cap, and rotation by an angle theta about y axis can be written as exponential minus I theta jy cap, where jx cap is the matrix 0 0 0 0 0 minus I and 0 I 0, and jy cap is the matrix 0 0 I 0 0 0 and minus I 0 0. These matrices, if we take their linear combination with some real coefficients, say theta 1 jx cap plus theta 2 jy cap plus theta 3 jz cap, where theta 1, theta 2, theta 3 are real coefficients, and if we exponentiate it, if we take its exponential, then this will be an element of rotation group SO3. So these are called the generators of this rotation group, and their commutation relations are written as, if we take commutator of jx and jy, here by commutator we mean if we have two matrices A and B, then their commutator is defined as AB minus BA. So commutator of jx with jy will give IJZ, commutator of jy with jz will give IJX, commutator of jz and jx cap will give IJY, jy cap. These commutation relations so they are they define the Lie algebra of SU2, which is isomorphic to the Lie algebra of SO3. In mathematics we call them Lie algebra. In physics they are called the infinitesimal generators of corresponding group. So the Lie algebra of these two groups, SU2 group and SO3 group, their corresponding Lie algebras are isomorphic, and their commutation relation are given by these expressions, these relations. So in this lecture we have seen that the SO3 group has corresponding Lie algebra, or as they are called infinitesimal generator in physics literature, and its corresponding Lie algebra is three-dimensional. It is generated by these three operators jx, jy and jz, and we have a map from this Lie algebra to the group, which is given by this exponential function. If we take any linear real linear combination of these matrices and we exponentiate them with a I factor of I, then we get an element of the rotation group.